Ça nous fait grand plaisir d'accueillir aujourd'hui au colloque du CRM une amie de longue date, Frances Kirwan, qui est une des géomètres les plus connus dans le monde. Already with her thesis, she established herself as a leading light in the theory of moduli spaces and also on the interplay between symplectic geometry and algebraic geometry. Since then, she worked on all aspects, basically, of moduli problems, notably with our own Canadian Lisa Jeffrey on the cohomology rings of moduli spaces. They did some extensive work together. Her work's been recognized in various places, most notably by her being asked to give a plenary address at the International Congress of Mathematicians, in her joining the exclusive club of British mathematical knights, and most recently in being named to the civilian professorship of geometry, the latest in a long line of illustrious shareholders. So today she's going to tell us about basically what to do with those unstable objects, which the rest of us have, in a sort of cowardly fashion, throw away before dealing with a problem, and she is bravely dealing with head on. So I'll just cede the floor to Frances and let her begin.
Very many thanks, Jacques, for a very kind introduction and kind invitation to give this talk, which is a very nice thing to do. It's just a shame that it can't actually be physically in Montreal, but it's great to be able to talk remotely. So what I want to talk about, as Jacques said, is moduli of understable things. So this is based on work with and work of a number of people. So many thanks to them. Oops, now I'm going to have to, there we go. Move to my next slide. So yes, I want to talk about moduli spaces and moduli stacks in algebraic geometry. So these arise in classification problems, moduli problems. So the basic point, if you like, is that classifying things in geometry, of course, we can't just do it using discrete invariants. We have things that vary with continuous parameters. So the sort of typical situation for a classification problem or a moduli problem is that we have some ingredients, we have objects that we want to classify. So the classical example, going back to Riemann, is compact Riemann surfaces, or essentially equivalently non-singular complex projective curves. And we have some sort of equivalence or isomorphism that we want to classify them up to. And we have to assume that we know what we mean by families of these objects parameterized by some base space. And ideally, we want to know when such families are equivalent. And so we want appropriate compatibilities between these things. And then in that sort of situation, you want to fix any discrete invariants, such as the genus for a compact Riemann surface, which are sort of locally constant on families, and then hope to be able to construct a moduli space. So ideally, equivalence classes of the objects, the set of equivalence classes of the objects with some nice geometric structure. And in some situations we can do this, and for non-singular projective curves we certainly can. And indeed, if we allow very mild singularities, so-called stable curves, we get a nice moduli space. But if we want to also include projective curves with more serious singularities, then we get big problems, and we can't construct a moduli space which is a nice algebraic variety. So, but nonetheless, we can still think about the moduli stack with these, including these singular curves. So that's giving a geometric structure in some sense, but it's a much nastier geometric structure, essentially coming from the moduli problem if it's set up appropriately. So the idea, the aim of what I want to talk about is that what we would really like to be able to do, or I would really like to be able to do, is given a moduli stack, to understand it by stratifying it into locally closed substacks, if you like, but such that these strata all do have nice moduli spaces. So there'd be an open stratum, which would essentially be the stable objects, probably, of whatever problem moduli problem you were looking at. And then there'd be other strata which would, well, ideally both have nice moduli spaces, coarse moduli spaces, and also maybe have a sort of locally constant normal structure within the stack. So how these strata should fit together will be some extremely complicated and nasty geometric structure, but you could hope that at least when you restricted to one of these strata, then you'd get locally constant normal behavior in a way that's maybe a little bit like Whitney stratifications when you're looking at singular varieties. So that's the rough idea or motivation. But let's just go. Oh, I keep doing the wrong thing. Let's go back to the nice situation where we've got moduli space of non-singular complex projective curves of fixed genus. So I'll work over the complex numbers all the way through, though it's not necessarily crucial. So this moduli space is very well understood, very beautiful, and it has a compactification, mg bar, which is the moduli space of stable curves of genus G. We'll assume that G is at least 2 for simplicity. And so a projective curve is stable. Well, I'll assume that all my projective curves are connected and reduced, but not necessarily irreducible. So a projective curve is stable if its singularities are at worst nodes and the automorphism group is finite, which basically means that if you've got an irreducible component which is a P1, a rational non-singular curve, then it has to have at least 3 points which are nodes where it meets the rest of the curve. So we get this nice projective variety, which is moduli space of stable curves. But the fact that it's projective tells us that we can't hope to add in curves with worse singularities and still get a nice projective variety in a non without introducing lots of horrible sort of Hausdorff non-Hausdorff sort of problems. So So yes, so how are we going to deal with this this idea of trying to stratify the whole moduli stack of, for example, projective curves? So the idea is to work with quotients by group actions. So moduli spaces and indeed moduli stacks often arise, well, at least locally for the moduli stacks, as quotients of parameter spaces by group actions. And so the very simplest example might be complex projective space, which we can describe in two different ways in terms of quotients. So we can think of it as a unit sphere quotiented by a circle action, and from that point of view we see that it's compact and it's Hausdorff and it has a nice structure as a Riemannian manifold. And then we can also describe it as non-zero vectors in Cn+1 quotiented by C star, and from that point of view it has a complex structure and the structures fit together, so we get a nice complex Kähler, a compact Kähler manifold. So that's a very simple example. Another is looking at smooth hypersurfaces of some fixed degree in projective space. So we get a nice quotient of an open subset of a projective space by the automorphism group of Pn, which is PGL n+1. So those work nicely, but of course we do have to be very careful here, because even if group actions look as if they're nice, they don't necessarily have nice quotients. So if we wanted to include all hypersurfaces, not just smooth hypersurfaces, we'd get into trouble. If for the projective space, if instead of Cn+1 minus 0, we tried to quotient the whole of Cn+1 by C star, then we'd get into trouble, because the orbit 0 is contained in the closure of every other orbit. So yes, so as I said, moduli spaces and stacks are often constructed in as quotients of linear algebraic group actions in this way. And so trying to find stratifications of moduli stacks with nice coarse moduli spaces is quite closely related to trying to find stratifications of algebraic varieties with group actions on, such that the strata have nice quotients. So if we're working with linear algebraic groups and over the complex numbers, as I said, then any linear algebraic group is just a semi-direct product of its unipotent radical, unipotent group, normal unipotent subgroup, by a reductive group, so GLN, SLN. And so we can think of a reductive group as, over the complex numbers, as just the complexification of a maximal compact subgroup. So we see that GLN and SLN are compact complexifications of unitary group and the special unitary group. So so we have examples of reductive groups that occur as automorphism groups. So you're often wanting to quotient by automorphism groups of things when you're constructing moduli spaces. And so the automorphism group of complex projective space, PGL n+1, is certainly reductive. But if you go to a weighted projective space, such as weighted projective plane, where you've got weights 1, 1, and 2, then you get non-reductive automorphism groups. So in this case, the unipotent radical is 3 copies of the additive group, corresponding to the fact that you can add quadratic functions in the variables corresponding to weight 1 to the variable or coefficient of weight 2. And then you have the reductive part, the Levy subgroup, which is isomorphic to GL2. So you get examples of both reductive and non-reductive groups coming in. When you're trying to construct quotients. And whether you're working with reductive groups or non-reductive groups, then finding quotients is not necessarily an easy thing to do, because you get non-compact groups. So even the simplest multiplicative groups, C star, the additive group C plus, are not compact. And that means that when they act on algebraic varieties, the orbits are typically not closed. So as we saw before, if you look at scalar multiplication on Cn plus 1, the orbit, which is just 0, is contained in the closure of every other orbit. So so that tells us that the topological quotient certainly doesn't have a nice geometric structure. But on the other hand, if you throw out the origin, then you just get projective space, and you do have a nice geometric structure. So geometric invariant theory, GIT, it gives us one way of telling us how to choose these bad orbits, like the origin in this case, and so to throw out in order to get a geometric quotient, which is an algebraic variety. So just as a brief reminder, Mumford's GIT, geometric invariant theory, developed in the 1960s. So I'll work over the complex numbers as before. So if G is a complex reductive group and X is a complex projective variety acted on by this group G, then you can get, then GIT tells you how to choose a nice open subset, which will give you a nice quotient. So more precisely, we need a bit of extra data. So we need a linearization of the action, so an ample line bundle, and a lift of the action to the ample line bundle. And so we can think of embedding X in a projective space and the action given by a representation. And then associated to X, or really to X and the line bundle, we get the homogeneous coordinate ring of X. And the linearization says that we allows us to get an action of the group G on this homogeneous coordinate ring. And so then we can look at the invariants for that action. So they form a graded complex algebra, because we started with a graded complex algebra. And because G is reductive, and we started with a finitely generated graded complex algebra, so we get the invariants form a finitely generated graded complex algebra. And that means that we have an associated projective variety, which we can think of as the GIT quotient. And so what does it look like geometrically? Oh, and it depends on the linearization, but in a way that's described by one of these wall and chamber decomposition pictures. So you can move the linearization around in the interior of some chamber in a decomposition of all the possible choices, and the quotient doesn't change. But then if you cross a wall between chambers in this wall and chamber picture, then the quotient can change in a particular way as you cross a wall. So strictly speaking, we ought to have notation that takes account of the linearization, but I'm going to forget that from now on. So what does this quotient look like geometrically? Well, because of the inclusion of the invariants in the homogeneous coordinate ring, we get a rational map in the other direction, and so that fits into a diagram. We can restrict it to the so-called semi-stable locus, and those are the points where at least one there's some non-zero invariant, some invariant that doesn't vanish at that point, and that means that this rational map restricts to a well-defined morphism on the semi-stable locus. And it's not at all obvious, but it's true that that actually that restricted map is a surjection to the GIT quotient, and it will be G invariant. It will actually give you a categorical quotient of the semi-stable locus. So it has a sort of universal property, which means that it only depends on the semi-stable locus and the G action on that. But it's not necessarily a nice geometric quotient. So you may have orbits that get semi-stable orbits that get identified in the quotient, but and in fact orbits get identified, semi-stable orbits get identified if and only if their closures meet in the semi-stable locus. But if you restrict a bit further to the stable locus, then you do get a nice geometric quotient, and the GIT quotient can be regarded as a compactification or projective completion. And you have links with symplectic geometry, so you can describe this this GIT quotient as symplectic quotient in terms of a maximal compact subgroup of the reductive group, and using a moment map. So so just as the projective space can be thought of in these two ways, quotienting by circle or quotienting by its complexification C star. So the same thing happens here. So you can think about the geometry from that point of view. So one of the really important things about Mumford's GIT is that you can describe the semi-stable locus and the stable locus without knowing what all the invariants are. So finding the invariants is really, really hard problem in general, but we have relatively straightforward criteria for describing the stable locus and the semi-stable locus. And exactly what it is not terribly important at the moment, but it's in some sense comes down to combinatorial descriptions and convex polytopes, and whether zero lies inside and in the interior of some convex hull of weights for the action. And so that's behind the variation of GIT, the wall and chamber picture that you get for when the semi-stable locus changes if you change the linearization. So we have this picture. We also have, in the case when the group is reductive, the possibility of getting rid of the worst singularities of the GIT quotient. So if we start with a non-singular x, then the geometric quotient of the stable locus will have relatively mild singularities. It'll just be an orbifold or Deligne-Mumford stack, just finite stabilizers. But the full GIT quotient can have much nastier singularities. But there's a sort of canonical algorithmic way to do blow-ups so that you end up with the situation that semi-stability coincides with stability for the blown up space. And so that means that you get the quotient of this blown up space has just orbifold singularities, and you don't do anything to the stable locus in this blow up construction. So you end up with an alternative projective completion of the quotient of the stable locus, which is, whoops, sorry, went the wrong way, which is this this partial desingularization, so this quotient of the blown up space. So it turns out that that when you go to non-reductive groups rather than reductive groups, then you have enormous problems with making GIT work in general. But for suitable non-reductive groups, then this picture, so the good case is when semi-stability coincides with stability, and then you get a nice projective variety, which is a geometric quotient of the stable locus. And then more generally, if at least you have some stable points, then this blow up construction can be generalized, as I say, for suitable non-reductive group actions. And so that's relevant to these, trying to find these moduli spaces for unstable strata in your moduli stack. So let's go back to the example of the moduli space of stable curves. So just reminding you of the definition of a stable curve, and we've got this projective moduli space, and it turns out that it can be constructed in many different ways, but in particular, one way to construct it is as a GIT quotient. And so this definition of stability for a curve then matches up with GIT stability. So the actual construction, well, there are different constructions, but it's not so important. You're looking at some pluricanonically embedded curves and the locus, or the closure of the locus of those in some Hilbert scheme, and you quotient by, you can think of quotienting by the special linear group, the associated special linear group. So you get a GIT quotient. So the idea is can we somehow use this construction or related constructions to construct moduli spaces of unstable curves? And so, as I said at the beginning, the aim is to try and stratify the whole moduli stack of projective curves or other moduli stacks, and to try and find discrete invariants of these unstable curves, but now not discrete invariants that are locally constant in families, but maybe more subtle discrete invariants that tell you which stratum you're on in this stratification, such that then we can find moduli spaces, nice moduli spaces of these curves in these particular strata, and to try and do that using these GIT constructions or other for MG bar, but also for other moduli spaces. So in particular, the other sort of classical example is moduli spaces of vector bundles over a fixed non-singular projective curve, or more generally sheaves over some fixed non-singular projective scheme of higher dimension, or moduli spaces of unstable maps rather than just unstable curves, for example. So for the sheaves case, the bundles and sheaves case, then it's been well understood for a long time how to stratify the moduli stack using the so-called hard and narrow Riemann type of the bundle or the sheaf. So this would be the sort of first step in trying to stratify the stack so that you you can construct moduli spaces of unstable things. But you can't just stop with fixed hard and narrow Riemann type. You have to refine the stratification so that you will get nice nice moduli spaces, because otherwise you're sort of if you look at all the bundles or sheaves with fixed hard and narrow Riemann type, then they will sort of collapse down onto the associated graded if you tried to construct a coarse moduli space of all of them, and it would be you'd forget a lot of the you wouldn't get the isomorphism classes. You'd have a much coarser equivalence relation. So that's the aim, and the point is that even if what you really want to end up doing is even if your original construction, as for MG bar and for moduli spaces of stable or semi-stable sheaves or bundles over a curve, even though that those GIT constructions use reductive groups and reductive GIT, if you want to understand the unstable ones, then non-reductive GIT comes in here. So yes, and I guess I shouldn't give the impression that just that you just have to turn the handle and use GIT and you get out. If you can do GIT appropriately, you get out the right answer. So you typically have to sort of guess what your stratification should look like in advance in order to set up your GIT problem so that you can get nice moduli spaces. So it's a back and forth sort of situation. So why do we need non-reductive GIT? Well, that comes in if you start with classical GIT, because if you've got a reductive group acting on some projective scheme, such as the one that I call K, which comes in when you're constructing MG bar by GIT. In this situation, if you've got a reductive group acting linearly, then you get this stratification of the projective scheme K, where there's the open stratum, which is the semi-stable locus, and then you have other strata. You'll just get finitely many if you've just got a reductive group acting on a projective variety, and so you've got these other strata which are indexed by points in a positive Weyl chamber for the group, and the unstable strata can be described in terms of using parabolic subgroups of the original group. So they can be constructed as the quotient by a diagonal action of the parabolic subgroup on the product G cross some smaller subvariety of the space that you're starting from. And that means that to construct some sort of quotient of an unstable stratum or an open subset of it by the group G, that you can think of as constructing a quotient of an open subset of this this other locally closed subvariety by the parabolic subgroup. And in some ways, that makes things more difficult because the parabolic subgroup is not reductive. On the other hand, it has some important advantages, which the main one is that the parabolic subgroup will have lots of, typically lots of characters, whereas the group itself, the reductive group itself, it might be SL of something as in the case for MG bar, and that won't have suitable characters. And why it's useful to have these characters is that when you have a linearization, then a lift of the action to a line bundle, then you can always twist the linearization, multiply it by a character, or indeed a rational character, because GIT doesn't really change if you replace the line bundle by a positive tenths power. So you can twist the linearization by a character or a rational character, and that doesn't change the underlying action of the group on the variety. It just changes the linearization, but it will potentially change the GIT quotient. And so so you can't, if you just take an unstable stratum and you try and quotient it by the group G, then you'll just get the empty set. You won't get any semi-stable points unless you change the linearization. So you want to change the linearization, but it's much easier to do that for the parabolic subgroup than for the group itself. So, oops, I've gone the wrong way again. There we go. So that suggests that it's worth thinking about what happens to geometric invariant theory if the group is not reductive. And so there are big problems because you can't, in general, even get started with the construction that I described, because we don't have necessarily finitely generated invariants in the non-reductive situation. And so we don't get a projective variety associated to the invariants. So there are various things that you can do. You can define a stable locus and a semi-stable locus, and with a geometric quotient of the stable locus and some sort of analog of a GIT quotient of the semi-stable locus. But there are lots of issues here. So the this GIT quotient, enveloping quotient at least, is not in general necessarily projective, and the morphism from the semi-stable locus to it is not necessarily onto, and you can't even try and get rid of one of those problems at the expense of the other by looking at the image of the semi-stable locus in the enveloping quotient, because it might not even be a variety. In general, it'll just be some constructible subset. And a big problem is that there's no obvious way of generalizing the Hilbert-Mumford criteria. So in general, there are lots of problems for non-reductive GIT. But if you work with suitable non-reductive groups and suitable situations, then you can do things. So one very simple example, which I will run through rather fast because I don't have a huge amount of time. So if we just look at the additive group, and let's assume that the action extends to a semi-direct product of the additive group and multiplicative group, where it's a non-trivial semi-direct product. And so then we can always find coordinates such that the multiplicative group acts diagonally and the additive group is in Jordan form, essentially. And that tells us that the additive group action actually extends to an action of SL2, and which so that the multiplicative group, the action of the U hat, the semi-direct product, will extend to SL2 cross an action of SL2 cross C star. And that means that in fact the U invariants and the U hat invariants will be finitely generated. So we can define an associated projective variety, and we can understand it geometrically, because roughly speaking, what happens is that if we take G to be SL2, then roughly speaking, the additive group invariants on the projective space correspond to the G invariants on this product of G and Pn quotiented by the diagonal action of C plus, which is a very nice action, so there's no problem there taking that quotient. And because the additive group action extends to the to SL2 to G, that sort of twisted product is isomorphic to just G mod C plus cross the projective space, and G mod C plus, that's just C2 minus the origin. And the invariants just, they're, at least locally, they're like holomorphic functions, and they're sections of a line bundle. And so they just, by Hartog's theorem, they just don't see the codimension 2 origin that's missing. So they all extend uniquely to C2 cross Pn. And then if you choose the linearization right, they extend to P2 cross Pn. So you find that this non-reductive GIT quotient can be described as a reductive GIT quotient. And so this is very closely related to the symplectic implosion construction in symplectic geometry, and gives you a nice geometric description for this this non-reductive GIT quotient. And in particular, it tells you that it gives you an examples showing that the morphism from the semi-stable locus to the quotient is in general not onto in this situation. So basically there are these boundary points coming from the origin in C2, which you don't see in the image of the semi-stable locus. On the other hand, if you quotient not just by the additive group, but by the U hat, the semi-direct product with the C star, then you can do some modifications of the linearization by multiplying by a rational character of the U hat. And if you choose them carefully, then the boundary points in this quotient by the additive group all become unstable for the induced action of C star. So once you quotient by U hat, you really do get a surjective morphism. And so we can generalize this picture. So if we have a unipotent linear algebraic group, which is graded in the sense that there's we can take a semi-direct product with a C star where all the weights of the C star action on the Lie algebra of the unipotent group are strictly positive, then if we have an action of this this extension U hat, linear action on a projective variety, then we can twist the action of the U hat by a character. And it turns out that if we do this in the right way, then we get GIT for the U hat action, which is nearly as well behaved as in classical GIT for reductive groups. So here's the theorem. So initially, let's forget about the bits I've highlighted in yellow. The theorem is saying that if you've got an action, a linear action of this U hat, this semi-direct product of unipotent group and multiplicative group, then if you at least if you have this condition star, which we can think of as a sort of condition that semi-stability coincides with stability for the U hat action, so it's not so important what it is. But if we've got this condition and we twist the action of U hat in by a suitable character, then we get the nice situation of finitely generated invariants, associated projective GIT quotient, and in fact we have semi-stability coinciding with stability, so we have it's a geometric quotient, and we have a very nice simple Hilbert-Mumford description. And if this condition star isn't satisfied, then at least you have some way of doing blow-ups so that you achieve this situation. So you get a projective completion of some stable locus, the geometric quotient of some stable locus, by doing some blow-ups and then taking a quotient. So that's if you're thinking about it from the point of view of the semi-direct product U hat. But on the other hand, if you want to just concentrate on the group U and trying to find some sort of quotient of the action of U on X, then one thing that you can do is you can think about the extension to U hat as in some sense a bit of extra data that gives you a generalization of what you mean by a linearization. So your linearization for the U action is not just a lift of the action to a linear action on a line bundle, but it's also an extension to this semi-direct product U hat, where the C star grades U, and a lift to a linear action of the U hat on this line bundle. And then what you can do is, if you want to have some sort of GIT type quotient by the U action, you can do the construction that I've highlighted in yellow in the middle of the theorem. So you can take the quotient by you can take the product of X with a P1 and quotient that by the U hat action, where U is acting trivially on P1 and U hat is just acting by the usual action of C star. And then if you get a nice quotient, maybe you have to blow up, but you get a geometric quotient of an open subset of X cross P1 or a blown up version of it. And so you can look at how that intersects X cross C star sitting in P1, and quotienting that by U hat is essentially the same as quotienting open subset of X by U. So you get some sort of some version of a stable locus for the U action in X with a nice geometric quotient and a projective completion that you can't necessarily, well, in general, you can't describe as a quotient of an open subset of X, but you can at least describe it as an quotient of an open subset of X cross P1, or indeed it's X cross C really. And so what you're doing is you're really adding at infinity the quotient of X by U hat to get a projective completion. So in some sense, that's you can think of it as a GIT type quotient by the unipotent group, but where the notion of a linearization has been generalized so that it doesn't just include the line bundle, but also this C star, this U hat. So so we can do this, and Yeah, so I am getting short of time, so I won't say anything much about automorphism groups of toric varieties, but they all do have a nice structure that means that you can apply this sort of setup. And more importantly, if we go back to the situation of a reductive group acting on a projective variety and this stratification, which I talked about before, or you can think of it as more stratification for a norm squared of a moment map, then you have these strata which you can try and take quotients of by looking at parabolic subgroups. And these parabolic subgroups have exactly the right form to be able to take quotients using this non-reductive GIT type construction, because they always have, the unipotent radical is always graded by a central one parameter subgroup of the Levy subgroup. And so you can always try constructing quotients of, well, it'll be an open subset of the stratum by reducing to a quotient by this parabolic subgroup, first quotienting by the unipotent radical using the central one parameter subgroup that grades, and then you'll get an induced action, residual action of the reductive Levy subgroup, which you can quotient by using classical GIT. So that's the basic idea for how we can apply non-reductive GIT to try constructing moduli spaces of unstable curves. So stratifying the moduli stack into strata so that you can quotient, you can find a nice quotient which will give you a nice coarse moduli space for the stratum. And I think I will skip over the two slides and just finish with saying also the case of moduli of unstable sheaves of over a non-singular projective variety. So again, we have a very well-known construction, a GIT construction of moduli spaces of semi-stable pure sheaves on a fixed non-singular projective variety. If you fix the discrete invariant, the Hilbert polynomial for some ample line bundle, and you get a GIT construction. And it's well known that if you're interested in fixed Harder-Narrow-Riemann type of sheaves, then you can construct this this GIT quotient in such a way that these sheaves of this fixed Harder-Narrow-Riemann type form a stratum in the stratification that comes from the GIT picture for the linear action of this special linear group. Modulo worrying about connected components and so on. So this is work in progress with Josh Jackson, who is a former student of mine, who was also looking at unstable curves, and Vicky Hoskins and Greg Bexley. So the idea is that then you use non-reductive GIT in this way that I just described, applying to parabolic subgroups of the associated parabolic subgroup of this special linear group, and you work out how to twist the action and construct moduli spaces of sheaves, and also you can generalize this to Higgs bundles. So Eloise Hamilton has been working on the Higgs bundles example as well. So you can get these moduli spaces of sheaves of fixed Harder-Narasimhan type. What you have to be careful about is that there are more choices involved. So what you're doing is you're fixing the Harder-Narasimhan type, and then you're saying, okay, well, I want to define some sort of stability or semi-stability for those sheaves of fixed Harder-Narasimhan type and construct moduli spaces of those. And so, as it typically happens, though not in the most simple cases, you then have to choose some sort of stability parameters or extra data to decide what you're to get these stable things of fixed Harder-Narasimhan type. And so that depends on a sort of a more complicated wall and chamber picture for these constructions. Okay, so I will stop there, and sorry for not giving the 5 minutes at the end for questions that I was asked to do. So apologies, and thanks for your attention.
Thank you very much. Are there any questions? And I think basically you just have to pipe up, because otherwise it's going to be complicated to
Hi, Francis. Nice to see you, and thanks for a nice talk. I was wondering if you could say a little bit about the singularities of the maybe just very slightly unstable curves.
Sure. So I think that the right way. So the first thing that you have to think about is what should be the analog of Harder-Narasimhan type for a singular curve. And so what seems to be the right way to think about this is that you want to think about the sort of associated graded. So for sheaves, then you have the Harder-Narasimhan filtration, and then you have the associated graded sheaf, which is just the direct sum of the subquotients, and you can, from a GIT point of view, you can think of that as being sort of limit under a maximally destabilizing one parameter subgroup of your sheaf of this Harder-Narasimhan type. And so there should be an analog of that in this situation of unstable curves. And the associated graded, the sort of limiting object, should be fixed by at least a C star, a multiplicative group, and probably by a bigger torus. And so when you're trying to understand what the associated graded for a singular curve should look like, it should be a projective curve with at least a multiplicative group's worth of automorphisms, and maybe a bigger torus worth of automorphisms. So there's a very nice paper by Popov from quite a while ago now, which is analyzing the projective curves that have, in fact, he was looking at all infinite curves with infinite automorphism groups. And And if you look at just irreducible ones, which he could reduce to very easily, then there aren't very many of them. And essentially the ones with GMs that we, automorphism groups that we want to look at, essentially they come down to rational curves with at most two singularities, which are going to be fixed by the multiplicative group, and then a very nice structure of what those singularities look like. So basically the associated graded has got to be made up of irreducible components, where at least some of these irreducible components look like these singular rational curves with GM automorphisms that Popov describes. And so so essentially what must be happening, I think, but has only been done carefully so far in some special cases, is that the associated graded, you're in some sense sort of bubbling off the singularities, so that you end up with the normalization of the curve, the resolution of singularities, with and then you've got the marked points corresponding to the points lying over the singular points, and then attached to those marked points, you'll have some of these irreducible, these singular rational curves with GM automorphisms. And I think the way that those sort of fit together and reflect the original singularities is to do with the blow up procedure that you can use to get from the singular curve to the resolution of singularities. So you know that you can get it by iteratively blowing up the singular points and repeating until eventually you get the resolution of singularities. And but so there are subtleties involved, in particular to do with these if you've got smooth P1s with just two nodes, two special points, then from the point of view of MG bar, you always sort of collapse those, and you ignore them, and that comes from the GIT construction. It's closely related to the fact that you're looking at the closure of this pluricanonical locus in the Hilbert scheme, and that's in some sense a well, I mean, you can also think about moduli of polarized stable curves or nodal curves, for example, and that was done by Lucia Caporazzo quite a long time ago now, and in the sort of construction of the universal Picard variety. And there you find that you have a slightly different a subtle stability condition, that where you sometimes allow some of those P1s with two marked points. And so yeah, I mean, I've gone on too long to answer your question, but there are subtleties there, and related, I think, to possibly having to choose some extra stability conditions. So if you've just got the situation where, so I guess I can, when you've just got unibranch singularities, then things become much simpler. So that goes back to EB in the 1960s, used classified unibranch singularities, and essentially he wanted to quotient by a non-reductive group action, but he had to resort to using slices rather than actually quotienting. But yeah, so so the unibranch case is simpler, and Josh Jackson looked at that in particular in his thesis. So you can look at cusps is the very simplest case, and that comes out nicely. But and you do just bubble off the cusp in some sense in that situation.
Okay, super. Thanks so much.
I had a question, which is how should I think of these quotients symplectically?
Right. So that's also very interesting. And so yeah, so that relates to what so this recent work that I've been, well, or project that I've been thinking about with a current graduate student, Yukin Shao, and so yeah, so if you've got this very nice situation where semi-stability coincides with stability, I mean, suppose we're in the unstable strata point of view, then essentially you I mean, if you took mu inverse, the inverse image under the moment map of the point that I call beta, which is the sort of the minimum point for the stratum, then that's giving you that's where you have to twist the linearization. You would twist the linearization to that in order to sort of describe the stratum, and that makes, then you only pick up the critical points, the associated graded. But if you go just a little bit beyond that, so that you're taking the inverse image under the moment map of sort of 1 plus epsilon times beta, then I think at least in the good cases, then that gives you a sort of symplectic description. But yeah, and I mean, maybe a better way to think about it is that, I mean, one of the way, the basic way that you prove this theorem about the U-hat quotients is you do induction on the dimension of the unipotent group, so that you can just reduce to the situation that you just do have an additive group. And then at least for the sort of ambient projective variety, you have an extension to SL2, and so you really do just have symplectic implosion for the U action, but you're not quite doing that because what you're really doing is that you're taking this product with a P1, and then you're well, and yes, then you're sort of yeah, so that gives you a bit more flexibility, but then you extend your action to an SL2 cross C star. But now, from a symplectic implosion point of view, as well as taking the product of X, or the ambient projective space, with P1, or really with C, you also want to take a product with P2, or really C2, in order to turn it into an SL2 action. And the trick is that you now have these C star, which is acting in lots of different places. And so as far as the sort of variation of GIT picture is concerned, you've got a sort of a two-dimensional picture where one way you're working with the maximal torus of the SL2, which is essentially telling you about the additive group action, but then you've also got another direction where you're working with the C star, which is sort of coming from the U hat. And so the fact that you're in this two-dimensional picture gives you a lot more options as to how you can shift things, and you can try hard to shift things so that you've got a that you've got all the conditions that you want, so that you make the things coming from the zero in C2, you can make them all unstable for the C star action, and then at the same time you can do some other adjustments that so you sort of get a picture where you're ranging from at one end you would get symplectic implosion, but provided that the action really does extend, and at the other end, and then you get a range of different quotients, a sort of variation of GIT.
But that circle for the U hat is acting, it's sort of acting on the normal directions of the in this close to the unstable points that are going to the graded object under the flow.
So it's quite complicated, because the crucial thing from a GIT point of view is that you want to make sure that the picture that you get out at the end does not depend on the power of the line bundle that you've chosen to get a projective embedding, and also it mustn't depend on the way you've chosen to extend the U action to an SL2 action, because you're wanting to end up with a well, in particular, you're wanting to then be able to iterate the construction to do C plus by C plus by C plus, and there's no way that you be able to do that if at each stage you're making choices and extending to SL2 actions, which won't necessarily be well behaved with respect to the you won't necessarily get nice induced actions. So it is a bit different from symplectic implosion, that in general, if you don't have an extension to some reductive group containing the unipotent group that you're interested in, then you have to be really careful that your construction at each stage only depends on the actual U hat action on X itself, rather than any ambient projective space, so on. So it just depends on the action of U hat on on X and also the lift of that to the line bundle. So you want to get sort of Hilbert-Mumford criteria that that just depend on this U action, well, this U hat action. So what you want to get is things like, and in the additive group case, you can always look at the closure of the C plus orbit, and that will always be a P1, and you can always restrict the line bundle to that P1, and you can look at its degree, and that will be a well-defined thing, which if you replace the line bundle by a tensor power, it'll just get multiplied by whatever the constant is. So that's the sort of thing that it would be fine to have in your in some sort of Hilbert-Mumford description of your semi-stable locus that would allow you to do things inductively. And so what you have is, in this two-dimensional picture where you're looking at weights of the torus in the SL2 and the C star, you're looking at sort of convex hulls of weights there, but you've got to be able to just look at properties of these convex hulls that are that you can describe in terms of somehow the structure of the line bundle restricted to the closure of the orbit of the point that you're interested in. So it turns out that yeah, symplectic implosion is right at the boundary of sort of what will work, and it will certainly be fine if you're if you start off with an action of your unipotent group which extends to a reductive action on the space that you're trying to quotient, but in general it won't. But you can get very close to it. So you can essentially, I think, get the sort of resolution of singularities of symplectic implosion where you quotient by torus at the on the boundary rather than the
Anyway, thanks a lot. Any other questions? If not, we'd just like to thank you for a wonderful talk and taking the time to come to speak to us from afar.
Well, many thanks for the invitation, and very nice to see you.
It's nice.
That's great.